Update on the baba ganoush. My husband just came in and said, good news, we have baba ganoush. Bad news, it doesn't taste very good. So I have that to look forward to for lunch today. I'm sure it's good. Okay, let's get started. So the next up, the topic next up, why do rocks change, right? We've said that when rocks undergo metamorphism, their texture and their composition changes, but why, right? Why do they change? And it all comes down to thermodynamics. Okay? So thermodynamics deals with the relations between energy and work, right? And the energy that determines the direction in which a chemical reaction will proceed, right? Which direction those chemical reactions will go is called Gibbs free energy. Now we're going to demonstrate with a familiar concept, right? Imagine there's a boulder at the top of the hill, right? And that boulder has a certain potential energy because of its height in the Earth's gravitational field, right? It's potentially could fall downhill, releasing that energy. So that's potential energy. By falling to the valley floor, that potential energy is lowered. Okay? So the natural direction of this process, therefore, is to decrease the potential energy. Gravity wants to carry that boulder down the mountain, and by doing so, it's going to decrease its potential energy. So gravity is just one form of energy in nature, but chemical potential energy is another, right? Just like you can understand that a boulder wants to roll downhill because of gravitational energy, chemical potential energy can cause reactions to move in a direction in the same way, right? So as that boulder is rolling down the hill, it's lowering the potential energy. Likewise, when chemical reactions proceed, they are lowering the potential energy, and we call this the Gibbs free energy. So just as the gravitational potential energy decreases when the boulder rolls down the hill, Gibbs free energy must decrease during a chemical reaction. Right? Now, if you look at this image, you'll notice that the boulder is not going to roll down the hill on its own, and that's because there's a little lip at the top of the mountain, a little bump. Right? So there's something hindering this result or this equation, this process from just happening. And that is the activation energy, right? That little bump that has to be pushed over, that's the activation energy that's required. So for a person to make this boulder fall down the hill, first they have to put in that activation energy, push it up over that little lip, and then nature will take its course and gravity will lower it down the mountain, right? But activation energy must be put in first. And in this figure, the activation energy is determined by the height of the lip on the ledge, right? The higher the lip, the larger the activation energy is needed, right? Same thing for chemical reactions, right? Every single chemical reaction has some sort of activation energy that is required to make that chemical reaction proceed. Now, to bring in another analogy with a person pushing over a large rectangular prism, notice that different orientations of this rectangle are more stable, right? So when a material is metastable, that means that it has a high activation energy, and that activation energy can be surpassed. It's just really hard. So it's probably going to stay where it is. It's probably going to stay stable. But if somebody supplies a lot of activation energy, it's going to become unstable. That block is going to turn on its corner. It doesn't want to stay there. That's not where gravity wants it. It's unstable, and it's eventually going to fall over and become stable again. And notice when it becomes fully stable, the potential energy is at its lowest, right? It's at its most stable orientation there. So any reaction that can take place naturally must lower Gibbs free energy. And the reaction does not reach equilibrium until the free energy reaches a minimum, until the materials of that reaction become the most stable, right? There's no way for that energy to lower anymore. So quickly conclude all of this. 3 important points. Reactions always take place in a direction that lowers Gibbs free energy, just like the boulder rolling down the hill. The equilibrium is only reached when Gibbs free energy reaches a minimum, right? When the boulder is at the bottom of the hill, when the boulder is stable. And applying this to Earth materials at equilibrium, temperature, pressure, and chemical potentials of all compounds must be the same throughout, right? That means the entire material has metamorphosed, the entire material has changed.